This is the fourth lecture of this week. What we discussed last class is we just introduced Arrhenius stress function. Today we will see that how that Arrhenius stress function can be used to solve boundary value problems. Now, you recall in terms of Arrhenius stress function phi, we have the phi satisfied, that this is the way phi is related to different component of stresses. So, with this relation the equilibrium conditions are already satisfied, and then if we have to make phi satisfy the compatibility equation, and the condition that phi must satisfy is this. Okay. This is the when these are the biharmonic operator. Now, this is for plane strain and this is for plane stress problem. We have discussed this. Okay. Now, in absence of body force, the right hand side becomes 0, and essentially we have this equation, and this equation is for plane stress and plane strain problem. In both the cases this equation is same, and this equation can be written as del 4 phi is equal to 0. This is a fourth order equation. Okay. Now, so this is the governing equation. Now, we have just only one equation, and that equation is this. Okay. Now, how it is to be now solved? You see, what the method we use will be using as power series method, where we start, we do not know what is the expression for phi. Only thing we know that phi has to satisfy this biharmonic equation, or if there is a body force, then the other equations. What we do is we assume some expression of phi written in terms of polynomials, and in that polynomial there are some constants. What we do is, now we substitute that polynomial in this equation and also the boundary conditions available. Based on that, we try to find out some relation between those constants and determine those constants using those relations. These steps will be clear as we let us demonstrate that through one example. Now, before that, the general approach will be, suppose the phi may be expressed in terms of power series Arato. Okay. This is the power series any. Now, this is essentially a polynomial. Okay. Now, it is the sum over infinity. It does not mean that we have to take the entire infinite series. We do not have to take, depending on the problem we may have to take third order, fourth order or fifth order, that depends on the problem. Okay. Now, and even we will see that the conditions available, some of the boundary conditions and some of the information about the problem that are available, which are obvious, and based on that information, some of the constants we can straight away we can make them 0. Okay. Now, for instance, if it is linear case, this expression becomes phi is equal to say A10 first is A00, the constant term A00 plus A10x plus A01y. So, this is a linear polynomial. Similarly, if we have to take phi as quadratic, then A00 plus A10x plus A01y, this is the linear term, plus the quadratic term A20 x square plus A11 xy plus A02 y square. Similarly, if we can take pi as cubic term, where all this term will be there, all this term plus addition term will be A30 x cube plus A21 x square y plus A12 x y square and A03 y cube. Similarly, if you can have fourth order, it is phi say it is linear term phi 1, phi 2, phi 3, and this will be phi 2 plus this. Okay. So, similarly, if it is fourth order, fifth order, we can have so many, we can express this power series in like this. These are essentially polynomials. Now, in all these polynomials, these are constant. These are constant. These are constant. Okay. And that constant needs to be determined based on the conditions that is available with us. based on the condition explicitly stated or based on the condition that we know about the problem. Now, you see, look at this equation. This equation is a fourth order equation, right? Del 4 phi is equal to 0. Okay. So, naturally, all these up to phi 3 means m plus n, if for m plus n less than 3, less than equal to 3, this equation is automatically satisfied. Less than equal to 3, this equation is automatically satisfied because it is a third order polynomial. Okay. So, naturally, when you differentiate it 4 times, then this has to be 0. So, for any polynomial up to third order, this condition is automatically satisfied. So, if for a problem we are assuming third order polynomial, then we do not have to really show that this compatibility condition is satisfied. Then in that case, what will happen? The compatibility condition is automatically satisfied because our polynomial already is less than the governing equation, and the equilibrium condition is satisfied by phi because it is satisfied based on the construction. But only thing we have to then use it the boundary conditions to find out the unknown constants. Okay. Now, you may argue at this point, if the equation is fourth order equation, then what is the point in having or in assuming the solution of third order, which is very rational logic. But you look at, our objective is not to determine phi. What is our objective? Our objective is to determine sigma. And how sigma and phi related with each other? Sigma and phi is related as this. If you recall that sigma x is equal to del 2 phi del y2, sigma y is equal to del 2 phi, I remove the body force term, x2, and sigma xy is minus del 2 phi del 2 phi del x del y. So, sigma and phi, that for that relation phi has to be at least quadratic. If phi is linear, suppose if we take phi is linear, then what happens? Sigma x, sigma y, sigma xy all are 0. So, in order to have non-zero stress field, phi has to be at least quadratic. If you take phi quadratic, then what happens? All the stresses will be constant. If you take phi cubic, the stresses will be linear. But phi, the minimum requirement is phi has to be quadratic. Okay. Now, if you take phi, if you assume phi as say cubic polynomial, compatibility condition del 4 phi is 0 anyway, it is satisfied, and then in that case the unknown associated with that polynomial, cubic polynomial, needs to be determined by the boundary conditions, and then you have an expression for phi. That expression gives you a non-zero stress field because that expression is cubic and your sigma, the relation between sigma and phi is quadratic. Okay. So, we can assume for a problem, we will be just demonstrating that through one example, we can assume quadratic polynomial, cubic polynomial. Even for quadratic and cubic polynomial, del 4 phi, that biharmonic equation, is automatically satisfied. Okay. But remember, if you have a body force, then right hand side is not 0, then that is not automatically satisfied, then you have to find out the condition, so that that gives you another equation. But for this problem, where the body force is 0, body force term is 0, cubic and second order polynomial automatically satisfy this biharmonic equation. Can we take linear polynomial? Means for m plus n less than equal to 1, can we take a polynomial? For instance, can we take this? This satisfy the compatibility condition, this satisfies this equation, but then can we assume the expression for phi as this? We cannot, because this does not give me any non-zero stress field, because in order to have the stress field, non-zero stress field, phi has to be quadratic. Okay. So, when we assume phi, we do not know what is the expression for phi. One thing we know, that phi cannot be linear. Another thing we know that phi can be quadratic or cubic, but in that case this biharmonic equation is satisfied. We do not have to show that they are that is satisfied, but for any other order polynomial we have to show that that polynomial satisfy the biharmonic condition as well. Okay. Now, let us demonstrate this let us first understand the procedure through an example. We will be demonstrating this procedure again and again in the context of different problems. So, let us in this class, since it is the first problem we are going to apply this array stress function method, take a very simple problem, very simple stress field, so that we understand the steps that need to be followed in order to apply this method. Okay. So, let us take an example like this. This is a plane stress problem, assume plane stress problem, plane stress problem. Okay. Now, this problem is what? This problem is we have a rectangular domain of 2h and a 2l size, and at 2 end you apply some in plane tension, okay, sigma 0 is that tension. Okay. Now, but remember the problem, this is the physical problem we have, there is no body force. Now, from this physical problem we have to translate this, we have to write the mathematical model for this problem. And what is the mathematical model? Mathematical model constitute 3 parts, if you remember. One is the boundary value problem, constitute 3 parts. One is the definition of the domain, and then the governing equations, and then the boundary conditions. Now, definition of the domain is now omega. The domain here is, say, use the different color. So, now, omega here is 2h cross 2l, okay. That is the domain. Okay. Now, the governing equation is del 4 phi is equal to 0, that is the governing equation. Okay. There is no body force. Now, in addition to that we need the boundary condition. Now, let us see what are the boundary conditions we have here. You see, we have 4 boundaries here. This is 1, 2, 3 and this is 4 boundaries. Okay. Now, boundary 1, what is the boundary 1? Boundary 1, we have sigma 0 is we have normal stress is sigma 0. If this is the normal direction, here also this is the normal direction. So, normal stress is sigma 0 and there is no shear stress on this boundary. Similarly, normal stress is sigma 0, there is no shear stress on this boundary. It means, can we say that sigma x at the normal stress is in the direction of x, all these unit normal is in the direction of x. So, can we take that sigma x x at x is equal to say plus minus L and minus L, if we assume our coordinate system like this, at any y, means on this surface at any y and on this surface at any y, that is equal to sigma 0. So, this is the boundary condition, boundary on the condition on the normal stress on this boundary and this boundary. Now, what other stresses, what are the stresses we have on the normal stress we have on this boundary, boundary 2 and boundary 4? Say sigma y, because that is the direction of unit normal at boundary 2 and boundary 4, sigma y for plus minus h means minus h at boundary 4 and plus h for any x, that is equal to 0. So, this is at boundary 1, boundary 1 and 2, boundary 1 and 3, this is as boundary 2 and boundary 4. Okay. These are the conditions on the normal stresses. Let us see what are the conditions on shear stresses. Now, you see, on this boundary there is no shear stress, on this boundary there is no shear stress. Similarly, on this boundary there is no shear stress, on this boundary there is no shear stress. Therefore, then sigma x y plus minus L at any y, that is equal to 0, and in this case sigma x y at any x plus minus y h, that is equal to 0. So, these are the 4 conditions specified at 4 boundaries. These are the boundary conditions specified as boundary 1 and 3, and these conditions are specified at boundary 2 and 4. Now, this is my complete description of the problem, complete description of boundary value problem. Okay. Now, we have to solve this equation such that the following conditions, following boundary conditions are satisfied. Okay. Now, once we have, this is the very important step. Once a problem is given to you, you encounter a problem like this, now you have to solve it. Governing equations anyway you have already derived, that is known, that is general, that is this equation is general for any problem you can apply this equation. But problem to problem, what is the main difference are the boundary conditions. Okay. So, it is very important to identify the boundary conditions. Now, no other boundary conditions given here. If you recall, we had 3 kinds of problem. One is where your conditions, boundary conditions are specified in terms of stresses, boundary conditions specified in terms of displacement, and the boundary conditions specified in terms of both displacement and stresses. This is the problem where boundary conditions are specified in terms of stresses. Okay. Now, once we have that, let us start with a very general expression. As I told you, there is this example is taken from a book. The list you can get that in the reference, but when you, or in many other books this example is given, but when you see that example, probably in many places you see that what is the expression of phi is directly given. Okay. But since this is the first problem we are solving, we have not yet gathered experience in doing this exercise. Let us start this by assuming a very general expression and then see how we may have many components in that general expression, but some of the components we can make them 0 by applying the conditions available, and then see how the solution can be obtained. Okay, let us start with let us assume phi is equal to take a cubic polynomial. Okay, phi xy, that is equal to, in cubic polynomial, the linear term, there is no point in having linear term because linear term does not contribute anything in computation of stresses. So, we will start with the quadratic term, and that is if you recall. So, a phi is equal to a20 x square, this is the quadratic term, a11 xy, and then a02 y square. This part is quadratic. Take the cubic term as well, a30 x cube plus a21 x square y plus a12 y square and plus a03 y cube. Suppose that is the expression of phi, as a expression of phi. In this expression, how many unknowns we have? We have 1, 2, 3, 4, 5, 6, 7 unknown, which are a20, a1 and so on. Now, since this is cubic equation, the biharmonic equation is biharmonic equation is satisfied. Phi is equal to 0. So, that is satisfied. So, we do not have to show that this equation satisfies this condition. But what we have to show is that this equation satisfy these boundary conditions. Okay. So, what we do now is we find out what are the conditions needs to be satisfied such that these boundary conditions are met. Okay. Now, for that let us find out the expression for stress. Now, if we recall, sigma x is equal to sigma xx is equal to del 2 phi del y 2, and if you write this, then this becomes 2a02. You can do this exercise parallelly and check a2, then we have this one 2a12 plus, then 6 A 0 3 y, and similarly we have sigma y y is equal to del 2 phi del x 2, that is equal to 2 A 2 0 plus 6 A 3 0 x cube x x plus 2 A 2 1 y, 2 A 2 1 2 A 2 1 2 A 2 1 y. Okay. And then we have finally sigma x y, which is minus del 2 phi del x del y, that is equal to minus A 1 1, then minus 2, we have x y term here, 2 A 2 1 x, then minus A 1 2, then we have this, there will be x here 1 2 y. Okay. So, this is these three equations we have, equation 1, 2 and 3. Okay. Now, you see these are the expression of stresses in terms of this constant. Now, this expression should satisfy all these boundary condition. Let us see, let us first start with this boundary condition, the boundary condition on this. Now, if we do that, now sigma x x expression is this. Now, let us write let us satisfy this condition on this boundary, on boundary 2 and 4, and if you do that, then what we get is, you check that 2 A 2 0 plus 6 A 3 0 x plus 2 A 2 1, 1 is C, and that is equal to sigma 0. There is some problem, you check it. Okay. That is equal to sigma 0. Okay. This is the stress sigma x x on this boundary. Similarly, we have 2 A 0, 2 A 2 0 plus 6 A 3 0 x, and then this is 0 actually. This is for boundary 2 and 4, this is boundary 2 and 4. So, this term becomes 0, and then it is minus 2 A 2 1 C, that term becomes 0. Okay. So, this is stress sigma y on this boundary number 2, and this is sigma y on boundary number 4. And from this what we get is, you can check, from this we get A 2 1 is equal to 0, and A 2 0 plus 3 A 3 0 x, that is equal to 0. Okay. Now, A 2 0 equal to 0 we have. Now, this is true for, if you recall this stress sigma y this stress, this is for any x. So, any x sigma y on this boundary at c is equal to, at x y is equal to plus c and minus c, at any x this condition is, this stress is 0, and therefore, this has to be 0, this has to be 0 at any x, and which gives you A 2 0 is equal to 0 and A 3 0 is equal to 0. Okay. So, then on this expression, what are the things you have? You have A 2 1 is equal to 0, A 2 1 is equal to 0, and then A 3 0 is equal to 0, A 3 0 is equal to 0, and A 2 0 is equal to 0, A 2 0 is equal to 0. Okay. Now, similar exercise if you do on this boundary, normal stress as well as shear stresses, we will check that all these constant will be 0. Similar all these constant will be 0. Okay. Only constant non-zero will be A 0 2. and if A02 is non-zero, means all these are 0, all these are 0, all these are all are 0. So, then essentially we have expression of phi is equal to A02 y square. You see. So, we could have started with quadratic polynomial, then also we could arrived at this. Okay. We started with cubic polynomial to show you this exercise that how to apply these boundary conditions. Now, one boundary conditions I have demonstrated here, but similarly you can apply the other conditions on the stresses and get the relation between different coefficients and find out their value. For this particular problem, those values will be 0 other than A02. You can try by starting with a fourth order polynomial as phi, and then do the exercise and then see what are the constants, what are the information about the constant that you can derive based on the boundary conditions available. So, now if phi is equal to this, then this phi satisfy the equilibrium, the compatibility condition, it satisfies the bound equilibrium condition, and then it also satisfies the stress, the traction boundary condition that is given to this, given for this problem. Okay. Now, once we have this, now let us move on. So, we have expression of phi as phi is equal to A02 y square, and then what we have is sigma x is equal to del 2 phi del y2, which is equal to 2 A02, and sigma yy is equal to sigma xy is equal to 0. Okay. From this phi we can derive that. So, if you take any point, sigma xx will be A02, which is constant, and sigma yy is equal to this. Now, expression of sigma xx is this. Okay. Now, this is constant, and this expression is true for any x and any y. So, if you take a point here, then also the expression of sigma xx this, if you take a point here, expression of sigma xx this, if you take a point here, expression of sigma xx this, if you take a point here, sigma xx expression is this, and this expression tells you that the stress is constant everywhere. If you recall when we introduced stress, we said that stress is a point wide description, and therefore, at every point that we have the stresses are different, but there could be some situation where the stresses are uniform, stresses at a different point is same. This is one example, but still the stress is a point wide description, that is still valid here, but every point the stress is constant. One example is this. Now, if the stress is constant every point, the stress at this boundary is also same constant. Okay. So, at this boundary stress is known, which is sigma 0. It means that sigma xx will be, so sigma xx will be sigma 0. Okay. And this is equal to 2 A02, and this gives us A02 is equal to sigma 0 by 2. Okay. And if this is, then what is the expression of phi? Then expression of phi is, phi was actually sigma 02 by 2 into y square, that is the expression of phi. Okay. Okay. So, we are almost done. So, we have calculated stresses. So, stresses are everywhere. So, the stress field in this case is sigma xx is equal to sigma 0, sigma yy is equal to 0, and sigma xy is equal to 0. That is the solution of stress. Now, once we have stress, we have to now next determine what is strain, and down near there we have to bring in the constitutive relation, the relation between stress and strain. Okay. And there, though, while calculating this, you take any problem, any material for the same state of stress, same bound, same conditions, same geometry, every time you will get the same stress distribution. But now, when we convert stress to strain and then strain to displacement, material property will come in. Okay. Let us find out how to determine strain now using the stress strain relation. Now, if you recall, for plane stress problem, the stress strain relation was epsilon xx was 1 by E sigma xx minus nu into sigma yy, okay, and epsilon yy is equal to 1 by E and then sigma yy minus nu into sigma xx, and this is equal to del u del x. This is how the strain displacement relations are defined when u and v are the displacement in x and y direction. Now, in this case only sigma yy is 0, that is sigma yy is 0. So, we can directly put sigma yy and then finally, we have this is equal to, and sigma xx is sigma 0, this is sigma 0. So, essentially what we have then, del u del x will be sigma 0 by E and then del v del y will be minus nu into sigma 0 by E. Okay. Now, from this if we integrate it, then what we have? We have u is equal to, then u is equal to, we have sigma 0 by E into x plus a constant of integration. Actually, now it is a partial integration, is the partial derivative here. So, the integration will the constant of integration, it is not constant in true sense, it will be, it will not be the function of x, it will be function of y, right, it will be function of y. Similarly, v will be minus nu sigma 0 by E into y plus g of x. Okay. Now, still, so this is the expression for u and v, but this is not the complete expression of u and v, because we have not yet derived, we need to obtain what is the g x and what is f y. Now, in order to do that, the third definition of strain, which is epsilon x y, that we may need. And what is that? If you recall, that epsilon x y is equal to 2 epsilon x y is equal to del u del y plus del v del x. Okay. That is how the shear strain is related to displacement, and that is equal to sigma x y by nu, where nu is the shear modulus, or sometimes we use g as well. Now, the sigma x y is equal to 0, we have seen for this case. So, this become 0. Now, this gives us, so if I substitute u and v from this expression, what we get is, we get this. If we get substitute from this expression, what we get it del u del y. So, this part will be 0. So, this becomes essentially del f del y, then plus del g del x, that is equal to 0. So, this gives you del f del y is equal to minus del g del x, that is equal to some constant. Okay. Now, suppose that constant is equal to w 0, okay, or omega 0, not w, omega 0. Okay. So, if del f del y is equal to omega 0, so now just quickly on the same here itself, if we can write, if del f del y is equal to del f del y is equal to omega 0 or minus omega 0, if we can take minus omega 0, then this gives you f is equal to minus omega 0 y plus a constant of integration, say this is u 0. And similarly, now del g del x will be your omega 0, this gives you g is equal to omega 0 into x plus constant of integration v 0. Okay. So, therefore, just if I have to write the entire expression, let us write the expression for u, then expression for u will be, final expression of u will be, so u will be sigma 0 by E into x, and V will be sigma 0 by E into y minus nu plus we have this term, this is for f del y and f y, this term minus omega 0 y plus u 0, this term will be minus omega 0 y plus u 0, this will be omega 0 x plus v 0. So, this is the complete expression for displacement. Okay. So, now we have stress, how the stress field is with the solution of the stress field. Now, we have the solution of displacement field. Now, here just before we stop, one important point, you see what is W 0, these what are these terms W 0, u 0, v 0, omega 0 and omega 0. U 0, v 0, it tells you what is the rigid body, when x is equal to 0, y is equal to 0 at everywhere, u 0 is the rigid body displacement in x direction and v 0 is the rigid body displacement in y direction, and omega 0 is the rigid rotation. So, this part actually gives you rigid body motion. So, this rigid body motion does not give you any strain. If you see, if you calculate strain from this displacement, only this part will contribute to the strain, this part will not contribute to the strain, which is very obvious. If I take any object like this and this object moves in this direction, rotate as rigid body, then this object will not experience any strain, the strain will be 0. So, therefore, now, but still they are unknown. In order to find these W 0, U 0 and V 0, what we need is, we need some more condition related to the displacement. Okay. And that displacement boundary condition, if we have, then we can determine this thing. So, if I just integrate strain and integrate the strain field and get the displacement, what we can have? We can have the displacement up to an arbitrary rigid body motion, and this is the arbitrary rigid body motion. Okay. In order to find out these constants, we need to have more condition associated with displacement of the problem. Okay. Now, so this is the solution of the problem. Solution of the problem, it is a very simple example, even where the stress field is constant. The idea here has not been to solve any particular example. The idea here has been to demonstrate the different steps that we need to follow for using array stress function approach for solving boundary value problems in elasticity. Next class, what we do is, next class will derive the expression, similar expression for array stress function expression in polar coordinate system, and then see some examples on polar examples related to that coordinate system. But again, next week when you talk about beam bending problem, and then next week when you talk about torsion problem, there will apply this concept, the similar steps, but in a different class of problems, means different in problems where we have different kinds of behavior. And another important exercise we will do next 2 weeks is, once we solve this, once we have the solution of those problems, beam bending problems or torsion problem, and then we compare those solutions with the solution obtained from strength of material, and then check what is the discrepancy and try to find out what are the possible reason for discrepancy. Okay. Now, at this point, though it is not the last class of this week, but since we are talking about array stress function, you see, we discussed earlier also that in most of the problem that we encountered, almost all problems that we encounter in real life, analytical model, analytical solution having in closed form is very difficult, and in almost all problems we have to go for numerical techniques, and numerical techniques is an indispensable tool in any engineering analysis. but still we are talking about array stage function, we are talking about analytical models, we are talking about solution closed form of simplified problems, because though numerical solution gives us very rigorous, very comprehensive understanding of the behavior of any structure, but for at the end of the day, in terms of translate your analysis result in terms of design provisions, and for quick understanding of sensitivity of different parameters, we do need analytical models. The exercise that we do in this next 2 weeks and this week essentially gives you a platform how to approach a problem if we have to derive an analytical model for a physical system. Okay, with this I stop today. See you in the next class. Thank you.